Today I'm going to go through the metric system and scientific notation worksheet that you have for homework. We're going to skip page 1 right now and go straight to page 2. On page 2 we're going to go over the numbers in scientific notation. The first thing we're going to do is learn a little bit about scientific notation. When we look at a number, the first thing we need to do is we need to know how many figures are significant. All of these numbers are significant. That last 0 is significant because it's shown even though it's not necessary. In order to move the decimal point to where it needs to be for scientific notation, there should always be a single non-zero number at the beginning and everything else follows. So we're going to move the decimal point 2 places, right there, to the left. So we have 1.5690 times 10, and we moved it 2 places, so we're going to put a 2. In problem 15, there are only 2 significant figures, the 1 and the 2. We need to move the decimal point, which is a presumed decimal point right here, 1, 2, 3, 4 places to the left. So our number becomes 1.2 times 10 to the 4th power. In problem 16, we need to move the decimal point 2 places to the right. Our number becomes 3.45. We moved it 2 places to the right, so we have times 10 to the minus 2. In this last problem, 17, all 3 of these numbers are significant, including that final 0. But these right here are not significant because all they do is show the magnitude of the number. We need to move our decimal point to the right until it's between the first non-zero number and the rest. So we're going to move it 1, 2, 3, 4 places to the right. So our number becomes 8.90 times 10 to the minus 4. Now let's move on to doing things the other way. In order to convert a number from scientific notation, we can start by writing the number as it is shown. Let's see if I can get this to work. But without the decimal place. Now the power over here, times 10 to the 6th, means we need to move the decimal point 6 places to the right. So the decimal point starts here, and we're going to go 1, 2, 3, we'll have to fill in a 0, 4, fill in another 0, 5, another 0, 6, and another 0. Now, the decimal point would be here, right here at the end, but we're not going to put the decimal point in because that will imply that the zeros are part of the significant figures. In reality, scientific notation gives us our significant figures. There are only 3. So we need to show that there are only 3 significant figures in our answer. So this number is 12,300,000. And these zeros over here are not significant. The next number, 2.5 times 10 to the negative 3, I'm going to write the 2.5 here. We need to move the decimal point 3 places to the left. So I'm going to go 1, 2, add a 0, 3, add another 0, and put our decimal point right there. So this number becomes 0.0025. Notice that there are 2 significant figures here, and there are 2 here. I added this leading 0 because it calls attention to where that decimal point is. Now let's take a look at the two word problems. Oh, no, let's instead take a look at the multiplication and division problems, addition and subtraction problems. The first problem here, 6.6 times 10 to the negative 8 divided by 3.3 times 10 to the negative 4. We can take a look only at the mantissa to begin with. The mantissa are the first numbers before the powers of 10. 6.6 divided by 3.3 is just equal to 2. Then we can take a look at our powers of 10, and when we're dividing, we subtract what's underneath from what's on top. So we have minus 8 minus 4, which is just equal to minus 4. So our number, 6.6 divided by 3.3, that's 2, and we'll add another significant figure since we have two figures there, times 10 to the minus 4. Okay? This number is our power. Likewise, when we look down here, 7.4 divided by 3.7, that is 2.0. In division, we subtract the top number, or we subtract the bottom number from the top number. 10 minus 3 is 7. So this is 2.0 times 10 to the 7th power. Now let's move on down to our first addition problem. Addition is a little bit different than multiplication. We can't operate on the mantissa if the powers are different. And you see that one of them is negative 7 and one of them is negative 8. If I write these in the normal manner, 1.56 times 10 to the minus 7 plus 2.43 times 10 to the minus 8, we see that we, because they have different powers, we can't add them up directly. So what I have to do here is I have to make the powers the same. So I'm going to take this power right here and I'm going to convert it into this power. And the way I do that, since I'm going down from I'm going up from minus 7 to from minus 8 to minus 7, I have to move the decimal point over by 1. When I do that, I end up with 1.56 times 10 to the minus 7 and 0.243 times 10 to the minus 7. Now I can add these up and I end up with 1.803 times 10 to the minus 7. Now I have a problem, and that is that the place value only goes this far with our top number. So I'm going to have to cut this off right here and not show this in my answer. So my answer is 1.80 times 10 to the minus 7. The 3 has fallen past our line of significance because its place value is too small. However, we could round across this line if that number was greater than 5. Now let's move on to the next one. We have multiplication. This is question number 30. Again, in this case, since it's multiplication, we can operate just on the mantissa 2.5 times 3 is just 7.5. In multiplication, we add the powers. So we end up with 2.5 or 7.5 times 10 to the 7 plus 6, or minus 7 plus minus 6 is minus 13. Now let's move on to the word problems. Number 32 says that the sun is 1.49 times 10 to the 11th meters away, and light travels at 3.00 times 10 to the 8th meters per second. Calculate how long it takes light to reach the sun, or to reach the earth. Express your answer in scientific notation. So the first thing that we need to do is figure out how we're going to approach this problem. What we need is a formula. Our formula that we're going to use is speed is equal to distance divided by time. What we're looking for in here, how long, is time. So we need to rearrange our equation. Time is equal to distance divided by speed. Now we can substitute. In our guess method, of course, distance and speed are our two givens, and time is our unknown. We've got our equation here, and now we just need to substitute. Time is equal to distance, which is 1.49 times 10 to the 11th meters, include the units, divided by, and I'm going to use the train track method here so that we can keep track of our units. And we're going to divide by 3.00 times 10 to the 8th meters per second. Now notice that seconds is flipped to the top in this equation because we're dividing. If we operate just on the mantissa and we say 1.49 divided by 3.00, we end up with 0.500. The answer is actually 0.49666 repeating. If we look at our power, we have 10 to the 11th and subtract the 10 to the 8th, and we get 3. So this is 0.500 times 10 to the 3rd power, and our units are seconds. Now the problem is this is not in correct scientific notation. I need to move my decimal point one place to the right. And when I do that, I'm going to change my power like so. So my actual number is 5.00 times 10 to the 2, or 500. But it did tell us to do this in scientific notation, so we're not going to show that. The importance of scientific notation is the fact that it shows all three significant figures right there. And we know that there are three significant figures because this number and this number show three significant figures. Our last one on this page, question number 33, says an electron has a mass of 9.11 times 10 to the minus 31 kilograms. Calculate the mass of 6.02 times 10 to the 23rd electrons. So looking at our guess method, G, our given, is our mass per electron, and the number of electrons. Our unknown is the mass. So from that, we can see that if we just want the mass up here, we're going to have to take this number of electrons and multiply it so that it will cancel with this. So our equation in our guess method is mass per electron times the number of electrons, so that electrons cancel and gives us just mass. Now we can substitute, and we'll plug in 9.11 times 10 to the negative 31 kilograms per electron. I'm just going to write ELEC. Normally I would write E negative, but I don't think I can do that with my finger on this iPad. Move this up here. And then I'm going to divide that by the number of electrons, 6.02, pardon me, I'm going to multiply that by the number of electrons, 6.02 times 10 to the 23rd electrons. You can see that electrons cancels with electrons, and it leaves us with the mass in kilograms. We know that we can operate just on the mantissa of these numbers, and 9.11 times 6.02 is equal to 54.8. When we multiply our powers, 10 to the negative 31 power and 10 to the 23rd power, we just add the negative 31 plus 23, and we end up with negative 8. So our number is 54.8 times 10 to the negative 8. The problem with this is not correct scientific notation. I need to move my decimal point from here to here, and in so doing I'm going to change this number to negative 7. I've moved my decimal place to the left by 1, so I need to reduce my negative number by 1 from negative 7 to negative 8. So my final answer is 5.48 times 10 to the negative 7, and of course our units were kilograms. Should have had units up here too. So our final number in this case, 5.48 times 10 to the negative 7 kilograms. I'll continue with page 3, 4, and 5 on the next video.